You will remember from the video on model-based methods more generally that we used the following formula to describe what these methods do. In this formula, X stands for additional information we may have about consumers. When we use finite mixtures of distributions, we do not have this additional information. So the formula loses the X. Everything else stays the same. We need to estimate the segment sizes pi and the segment-specific characteristics theta. What does this mean that we lose the x's? It means that we're using the same segmentation base which we use for distance-based methods, usually a set of variables relating to the same construct. One example could be a set of 15 vacation activities where tourists indicate whether or not they engaged in them. This would lead to binary segmentation variables. If we have such a dataset, we can use finite mixtures of binary distributions. If we would now ask tourists for those vacation activities they engaged in, how many minutes they spent on them during their holiday, we would get metric segmentation variables. With metric segmentation variables, we can use finite mixtures of normal distributions. So the only difference between mixtures of normal and binary distributions is that the segment-specific characteristics have to be estimated in a different way. Let's have a look at finite mixtures of normal distributions first. The segmentation variables are metric. A set of normally distributed metric variables is described by their means, their variances, and their covariances. As a consequence, we need to estimate segment-specific means, segment-specific variances, and segment-specific covariances between all pairs of segmentation variables. You can imagine that's a lot of parameters to estimate. To make things a bit easier, we can choose from a number of restricted models where the structure of variances and covariances are restricted. They can be restricted within segments, across segments, or both. For example, if we restrict within segments, we can set the covariances to 0. This means that the segmentation variables are assumed not to be correlated within segments. Restricting across segments might mean, for example, that we set the variances and covariances as equal across all segments. There are a total of 14 possible restricted models. When you run finite mixtures of normal distributions using package mClustern-R, all 14 models are calculated by default. The best solution, according to the BIC, is returned. Let's now have a look at finite mixtures of binary distributions. The segmentation variables are binary. A set of independently binary distributed variables is described by variable-specific agreement levels. For example, each tourist tells us which vacation activities they engaged in and which they did not engage in. Across the entire sample, we get a percentage of agreement with this vacation activity. As a consequence, we only need to estimate the segment-specific agreement levels. This makes the model a lot less complicated. Finite mixtures of binary distributions are also referred to as latent class models. Finite mixtures of normal and binary distributions assume that market segments are different with respect to their segmentation variables y. Finite mixtures of regressions do not. They use additional characteristics x about the consumers and assume that market segments are different with respect to the relationship between x and y. So first of all, we use the complete formula again, which includes x. An example of when it might be useful to use mixtures of regressions is when we assume consumers may differ in the price sensitivity. The data we have is the prices of products Rx's, and whether or not each consumer purchased these products at those prices are Y's. The relationship between our X's and Y's is the price sensitivity, and this is what we use to extract market segments. Depending on the nature of Y, we can use a range of different regression models to relate X and Y. Common choices are a linear regression model for metric Y's and a binary logistic regression for binary Y's. There are many possible extensions of finite mixture models. One is to use descriptor variables as part of the segment extraction. You may recall that typically we use segmentation variables to extract segments, and then we use descriptor variables to describe the segments. With so-called concomitant variable models, we can simultaneously model segmentation and descriptor variables. This is not done by simply pretending that the descriptor variables are a few additional segmentation variables. Rather, the segmentation variables still drive extraction, but including the descriptors in the model usually leads to segments which are more distinctly different with respect to these descriptors. This is great for managers because it makes it easy to target those segments. Another extension can address the problem that we often get pure response style segments. Such segments are characterized by how respondents use the survey response scale. When people are asked to answer a set of survey questions on ordinal multi-category scales, their response is often a mixture of their true answer and their response style. For example, we may ask consumers for their opinion about a product. The true answer is their opinion. The response style manifests in their preference for ticking certain response options in surveys. Some respondents like to use the extreme answer options, others tend to use midpoints. Response styles contaminate data. Of course, the best approach is not to collect data in a way that is prone to contamination by response styles. However, sometimes we are faced with the situation that we have data which is likely to contain response styles. Here, we can use model-based methods which account for response styles. The basic idea is to simultaneously extract groups of consumers who are similar in terms of their true answers, their opinions for example, and groups of consumers who have the same response styles. Once they are identified, we can eliminate response style segments and interpret only segments based on true answers.